Good morning, everyone. Welcome to uh, our lecture. Before we get started with our lecture this morning, I want to bring to your attention that Thursday we will have exam, midterm exam number 2. I did share the study guide and the formula sheet on Canvas yesterday. I plan on making quiz number 6 or quiz for number 6 available today. You will also use this question to prepare for the exam. Please use there was a mock exam, be honest, and try to answer the question on your own. Nick prepared a mock exam similar to what you will see, not exact, not word by word, but I looked at the question and they pretty much covered the concept I want you to master in midterm or for midterm exam 2, midterm exam 2. Without wasting my time, I don't think today will be a long lecture. I want to finish only chapter 6 and wait until next Tuesday to start 7. Pretty much what is remaining in 6 are some of the concept you have covered before, electron configuration, just going through that. Let me share my screen and show you where we were with the PowerPoint slides. We went as far as section 6.4, that is the de Broglie wave equation, and before that we looked at the Port's model of an atom, and he was able to connect this with where we are. Recall hydrogen Port's model of an atom, or to be specific, this is what we know so far. The Port's hydrogen model, all right, model of atom. We proposed that electrons move around the nucleus, all right, following what we call the orbits. And his explanation was based on the line spectra. We talked about the hydrogen line spectra using the Rydberg equation. He was able to calculate the wavelength of those spectral lines. Now, Paul you start to explain that whatever they were looking at the line spectra for hydrogen, it was because of electrons transitioning from excited state to what we call ground state. So picture this as electron moving around the nucleus. This is Paul's model of an hydrogen atom. Got to be specific that Paul only talk about hydrogen. Now, somebody else in section, I want to pick up from section 6.4, somebody else by the name Louis de Broglie, he was a French physicist, proposed that if he agreed with Paul, or, you know, other contemporary around Paul, that actually electrons move around the nucleus. And he said if electrons, or rather, if light behave, this is what de Broglie, you see here, he was a French physicist, theorized that if light is behaving like a wave, all right, if light behave, all right, you say if light behave like matter, that means And then why not the matter? Then matter like light. What he was trying to explain here is if light has wavelength, amplitude, and stuff like that, he proposed also that matter can also have a wavelength. And in this case, we call this de Broglie wavelength. It's not the wavelength we talked about, the wavelength of light, or we call this de Broglie wavelength. We call this, you will see this de Broglie wave length, and this is for what? This is for matter, and what he was proposing was for what? For an electron. Is given by this equation. He proposed that this is the equation for calculating the wavelength of matter. Anything you can think of, like something you can feel. You'll see in the problems talking about, baseball, talking about, aeroplane, moving at a certain speed. So in other words, treating matter as what? As light, which means we can calculate what we call de Broglie wave equation. Let me just explain or show you what these constants stand. This is the same Planck's constant we have been dealing with. This is Planck's constant. You don't need to memorize this. You'll be given in the exam 6.62 6 times 10 raised to negative 34 joules per time a second. This is the same Planck's constant H, the same Planck constant we saw before. The M is, this is mass in, remember, mass in kg, mass in kilogram. Most problems will give you masses in other units other than masses. If you're given a mass in grams, you got to change to kilogram. If given the mass in milligram, you got to change to kilogram. If given in pounds, you got to change to kilogram using appropriate conversion factor. And then this one, this is, it could be speed. You may be given speed or velocity. Velocity, you'll see this term velocity, and it is in meters per what? Meters per second. I want to circle the units here so that you know which unit you will be dealing with for velocity, and for mass, it's got to be in kg, it's got to be in kilogram. The reason why is we will have to reconcile with the SI unit for energy and the wavelength, which we saw earlier on, that 1 joule equals to kilogram times meter square, all right, of second square. We saw this earlier on. This is a conversion we'll use in changing to get the wavelength, So
can you go back to the last slide really quick for me?
Hello?
Can you go back to the last slide for a second? The previous slide?
Right?
Yes, that one. Does that constant say times 10 to the negative 3x?
No, this is times 10 to negative 34. Planck's constant H, this is 6.626 times 10 raised to negative 34. And then the units is joules times seconds. That is the Planck's constant, and you'll be given that. You don't need to memorize that unless it is homework. They expect you to flip the page and say, hey, where's the Planck's constant? So
okay, thank you.
That is what it is, yeah. This is J times S, J times S times 10 to negative 34. And so it's the same Planck constant we used before. So problems, it will be very straightforward that calculate the de Broglie wavelength. Problems on de Broglie has to do with de Broglie. Otherwise, it will not be an open end that calculate the wavelength, even though you may use the information given there that it is matter. Matter is something you can see with your naked eye. So for most problems on de Broglie, it is something you can see. And in this case, it has to do with the electron. The challenge in this is now there's some compound concept you need to apply in solving. It's not going to be always mass in kilogram. It's not going to be always velocity in meters per second. You have to use prior knowledge in calculating or doing the conversion. Maybe solving one or two problems on this will help on how to calculate the de Broglie. This is, underline the word de Broglie, so I know we will be using this equation, not flipping, h as Planck constant, mass times velocity. So if I look at the in meters, the mass here I've underlined, it is given in, so mass here got to be in grams, kilograms, 0.5 kg. I just converted that to kilogram. Speed, this is the same as velocity. It is in meters per second, so I don't need to change that. So I'll plug in the constant 6.626 times 10 raised to negative 34. Let's see how we reconcile the units of mass 0.025 kg, all right, and then times the speed is not square, but velocity, same as speed, 5.0 meters per second. Now, this is the conversion to change to units, to change to meters. That the conversion factor here is times, all right, 1, all right, K, meter square per second square. All right, so second and second will go with the square for that. We cancel that and that too. To joule, this is 1 joule. Joule and joule, I'm using this conversion factor to change or reconcile the units. And then the kg here will go with the kg, meter will go with 1 meter and you'll remain with 1 meter. You don't need to just showing you that. If you know how to plug in the values you have, the numerical values, it will cancel, the unit will cancel along. So the key thing is what I've bolded on the problem is what you need to pay attention. This might be in miles, might be in kilometers, might be in other units. Mass can be in different unit as well. I'm looking for my calculator. It's right here. I want to just key in on my calculator. At the top is the Planck constant 6.626 exponential negative 34. All right, divided by 0.025 divided by 5. This is, I get 5.3 times 10 raised to negative 33 meters. So the wavelength for the de Broglie wavelength for this object moving at that speed 5.33 times 10 raised to negative 33. Be careful with the multiple choices. Sometimes you may have two multiple choice with the same numerical value. This could be positive and negative, and somebody will say, oh, maybe, especially when you key in here and forget to put negative 34 on the Planck constant, you'll end up with the wrong. This will be positive, and for scan tone, it will not show or you will not get partial credit for showing your work. So that is what the de Broglie was saying, that if you guys, he was just telling guys that if light is behaving as matter, and then matter can also behave as light, and that means we can calculate the wavelength. We can calculate the wavelength. Now, since he proposed, since this de Broglie equation in light with an electron, remember, de Broglie now is redefining the Port's model that, if matter behave as light, that means electron is moving. It's no longer a circular path. It's no longer a circular path the way Port's proposed, but Heisenberg, the guy you see on the screen here, say, hey, look here, it is not possible. That is where this uncertainty, uncertainty means it's impossible to know with certainty the position of an electron moving around the nucleus. We cannot know the position and at the same time know its speed. In this case, he came up with the uncertainty principle that there is uncertainty in position, uncertainty in velocity, which when multiplied by mass, we end up with what? The uncertainty in both position and momentum, which states that there is the minimum which we cannot tell the position based on this equation. This is not equal, but greater or equals, in mass, that this is greater and equal. This change or delta x is, this is an certainty in position. And this is in velocity, that we cannot tell the position and at the same time the location of an electron in what? In an hydrogen atom. The moment the electron is, if electrons are moving constantly, then how do we know the position? So the more we know the other, we compromise the other component, which is the speed and the velocity. Now, in uncertainty principle, this is the same Planck constant, all right, the same Planck constant we talked about. We use P4. And of course, you know this from mass. This is 3.1 for 3.14. And the point is that the electrons cannot be, or electron cannot be, we cannot tell the position of an electron and at the same time the speed of at which it is revolving around the nucleus. Two questions from this uncertainty principle is, and in position, it is just making the uncertainty in position to be the subject of the formula, that this change in position. We're talking about the position here. Change in X uncertainty is greater or equals to Planck's constant over 4 times pi times mass times change in velocity, and we have to change also mass in kilogram. This is always mass in what? This is mass in kg, and this is the speed in meters per second. Meters per second. So question is, calculate the uncertainty in position of an electron moving in this, and then of course pi, plugging in the values in on your calculator should give you the equation. Uncertainty in velocity, because there are two things. We cannot know the velocity is greater or equals to Planck's constant of 4 times pi, which is 3.14, times mass in kilograms times uncertainty in position, which is X. So you'll be given either of them and you are asked to calculate the uncertainty. And the point here is, all right, if actually de Broglie was right that matter behave as light that it has a wavelength, it travels in a wave manner, and then there is no way we can know what position and the velocity for that. We can calculate the uncertainty in position, uncertainty in velocity, in particular subatomic particles. You'll see problems on subatomic particles. And you will speak even either the masses, or you can you'll have to look at the table at the back of the text. We have the mass of an electron, mass of a proton. Before we look at P, let's look at A. Using the Heisenberg uncertainty principle, calculate the uncertainty in position of 1.50 milligram. A mosquito moving at a speed of 1.40 meters per second, if the speed is known within plus or minus 0.0 plus or minus 0.01 meters per second, meters per second. Here is a typical problem. Remember what I say in terms of mass. Mass has to be in what? Look at this. Mass has to be in kg. Velocity has to be in, uncertainty in velocity has to be in meters per second. For A, delta X, that is uncertainty in position, is greater or equals to 6.626 times 10 raised to negative 34 over 4 times 3.14 times uncertainty in velocity. Or rather, first of all, let's see the mass. Mass is given in kilogram, and what this means, 1.5, you need to change that. 1 milligram equals to 1 times 10 raised to negative 3 grams times 1 gram equals to 1 times 10 raised to negative 3 kg. What I'm doing here is changing the mass to what? Changing this mass to kg. So 1.5 0 times 10 raised to negative 6 kg times not velocity, but uncertainty in velocity, which is 0.01 meters per second. To reconcile that, there was that unit we use. We use this to convert 1 joule equals K times meter square over square, like that, to change to units, So this mass is not what you will just plug in the way it is, but mass has to be in kg. Uncertainty in velocity, this is not a velocity. This is not what you need to plug in the uncertainty in velocity. This is the uncertainty in velocity which is used in the equation, So let's see what this will be in terms of just plugging in your calculator. Let me erase here and plug it in a calculator. So 6 point what? 6 point 626 exponential negative 34. I do have at the top. Please get to know your calculator. Divided by 4. Enter. Negative 6. 1 point, all right, 1 point, you get 1.6, no, 6.626 exponential negative 34 divided by 4 divided by 1.5 So 4 point, I get 4.1 4 5. Let's say 5 times 10 to negative 17 4 negative 27. This is 4.4 times. This is 27 for that. So you plug in the calculator and get this is equals to you change in what? Change in position is greater or equal to 4 point. Change in greater than equal to 4 point. So remember to use the uncertainty, not the speed, For subatomic particles, such as moving an electron, the challenge here is knowing, wherever you are given that, sometimes they expect you that you have used the text, find the mass of an electron. All right, it turns out that the mass of an electron, it is given mass of an electron. Yes, all right, thank you, Lauren, for this negative 27 because of the one significant figure. If you write that is 4.27, that is right. That is right. This is 27 and it is 4 point times 10 to negative 27. It's because of the one significant figure. You'll see in the multiple choice 4.0 times 10 to negative 27. Change in X, same, yes, the same thing. Mass of an electron for B, calculate the uncertainty in position of mass of an electron. It turns out mass of an electron is 9.11 times 10 raised to negative 31 kg. Mass of the proton, these are the subatomic particles, you will be given 1.67 times 10 raised to negative 27, all right, 27 kg. Neutron, 67 times 10 raised to negative 27 kg, just in case you are given in a problem, let's say homework, and say, where I'm not given the mass of an electron, I don't have the mass of a proton, I don't have the mass of a neutron, how will I find that? It is given at the end of the, at the back of the text, you have this information. In the exam, you'll be given this to save time. Know that the masses has to be in what? In kg. So for B, or question 2, calculate the uncertainty in position of an electron moving at a speed of 3.00 plus or minus, all right, plus or minus 0.01 times 10 raised to negative times 10 raised to negative, no, positive 5. So the uncertainty here, look at this uncertainty again. It is not about the entire speed, just the way we had it here, we have that as well. So uncertainty in position, x, Planck's constant, over 4 times pi times mass of an electron. Plugging this is 6.6 to 6 times 10 raised to negative 34. 4 times 3.14. This is an electron, so it's 9.11 times 10 raised to negative 31 times 0.01. Please check, you should have this 3 times 10 raised to negative 6 meter. Please check that you get that for part P, for part P. So that is all one.
Sorry, why would it not be the 0.01 times 10 to the 5th as the uncertainty?
Oh, because it is right here. This is it's not 0.005. All we know is within the uncertainty right here. The significant figures we use on this side of the equation. Remember?
I see.
Yes.
Okay. Awesome. Thank you.
Mm-hmm. All right. So that is what? That is the Heisenberg uncertainty, that we cannot know the position, and in particular, the subatomic particles here. We are looking at the atom. Now, that sets the foundation of where we are right now in terms of the model of an atom, the electronic structure. That is the topic. Chapter 6 is electronic structure of an atom. And the current model of an atom is what we call quantum mechanical model of an atom. And of course, it will talk about what? We'll talk about the, we have looked at 1, Bohr model, and 2, the quantum mechanical model of an atom. This is the subject of 6.5. That what we know now is electrons are moving around the nucleus like a what? Like a wave, and we cannot know the position, we cannot know the where it is, but we know they are right there. Now, our section 6.5, since we are coming in now with the understanding that it is not possible to know the position and the speed. This was Schrödinger or Schrödinger, excuse my pronunciation, was an Austrian physicist who reconciled now the wave property and the particle property of an electron. Is trying now to do what? To say, how do we really know where the electrons are? It's like giving an address where we can find exact location of an electron in an atom, and he developed some, some mathematical equation we call wave function. It is beyond the scope of this call. This is called the quantum mechanics, which only give the probability. Since we do not know, the solution of wave function give rise to what we call the mathematical equation give what we call the wave function. And this solution, the solution for the wave equation is u squared. Forget about the symbol here. This is just what or represent what we call orbital, or the probability of finding an electron. If you look at this diagram, if this is the model of hydrogen atom, we are now redefining the Bohr's model of an atom, that since we don't know where the electron is, there is a region within an atom where there is high probability of finding an electron. If you look as we move away from what? From the nucleus, the probability of finding an electron gets low and low and low. So we are talking about probability of finding an electron within an atom, and we call that orbital, which is different from the orbit. Orbit is just a circular path around the nucleus, around an object. Path, orbit. But orbital is a region of space. Let me define this. Orbital. In an atom where there is high probability of finding an electron. We call that orbital. Orbital is a region where there is what? High probability of finding an electron. The dark, the more intense color is high probability. Away from the nucleus, low probability. So now we define an orbital using what we call quantum numbers. An orbital is described by quantum what? It's just like giving an address. If you live in an apartment or a home, if we want to know where you are, we will have to follow the address, the numbers, right? If it's an apartment complex, there might be a name, but we have to give the apartment what? We are mailing an address. So right here, the orbital, an orbital is described by what? By quantum numbers. And these quantum numbers, all right, these quantum numbers are based on the line spectra we talked about earlier on. We'll see those, but these orbitals, or an orbital, if it is one, or orbitals, we describe those using what we call quantum numbers. And it doesn't change. There is what we call the quantum number here is we have what we call principal quantum number. There is angular momentum number. All right. And each one of them represent energy level 1. Let's say this principal number 1, number 2, shell number, principal, take the values. We use this, and principal quantum number, we use not 0, we don't have 0. These take values 1, 2, 3, 4, all the way, you know, moving away from the what? From the nucleus. So sets of 3 quantum numbers. First is the principal quantum number n. It's the same as energy level. Let's just recall that energy level 1, energy level 2, I used this before, n equals to 1, n equals to 2, n equals to 3 for principal energy level 1, energy level 2. And this represent, it shows the energy or represent the energy of an electron. It corresponds to what? The Bohr's model, we use n equals to 1, n equals to 2, n equals to 3. The values for n is greater or equals, which is the same as 1, 2, 3. It cannot be 0. The electron has to be somewhere. So you cannot have 0. Let me go back here again, and you need to know what they represent. N represent the what? The electron. Sets of orbital, these represent energy. Principal energy level 1, principal energy level 2, energy level 3. And then quantum or angular momentum quantum number. Angular momentum number, all right? We represent this using L, and it takes values L, it takes values 0, it takes values 0 all the way n minus 1, n minus 1, zeros all the way to n minus 1. Which means we need to know n in order to know the values for angular momentum number. So if this is n 1, 2, 3, and of course going to 4, maybe we have 4 there. You are familiar with S, P, D, and F. F sublevel. We call sublevel. S, P, D, F. These represent, they coin this letter sharp, profound, fine line based on the line spectra from what we took up earlier on. So it take values. Let's take the values from 0 all the way to n minus 1. What does this mean? If you know the value for Ln, e.g., let's see how this works. If n equals to 1, L can be 0, and then all the way to n minus 1 is 0, so it's gonna be 1. But if n equals to 2, values for L could be 0, 1, because n is equals to 2, so n minus 1 is, this case, 1 minus 2. I'm trying to explain what this means, what I mean by this, that you need to know the value for what? Value for n first. So if n equals to 3, L could be 0 all the way to n minus 1, which means 0, 1, and then 2, of course. So this is S, P, and then S, P, 0, 1, 2. That's how you find the angular momentum, the possible. What I mean here are possible, not all of them, these are possible values. If n is equals to 3, we can have 0, we can have 1, we can have 2. And remember, the values I'm getting here, you need to commit to your memory. What I have here, that if L equals to 0, and then if n equals to, this I meant to say this is D, and here is F. Sorry about that. This is what I meant to say. This D, and then F, and then G. We don't go to G. You need to remember that if n equals to 4, if n equals to 4, possible values for L is 0 all the way to n minus 4, which is L in this case is 0, 1, 2, and 3. And if I look at these represent S, P, D, and F, sub-level. These represent the shape. Quantum numbers define the shape. You need to know what each one of them represent. In this case, they represent the shape of L is the shape, S. Remember S, spherical, that is where we are going. Remember P, orbitals, they are dumbbell, the cloth. So L allowed values range from 0 to n minus 1. These are possible values. To know how this works is when you are given the values for n, you can predict the possible values for L, and they are represented by these letters. You are familiar with this. This is where we are going with the electron configuration. And then magnetic quantum number, the last quantum number is magnetic quantum number. We call M's of what? M's of L. You read this as, this is read as M's of L, M's of L, all right? Possible values for M's of L, take values negative. This is negative L. Let me just try my pen here a little bit. This takes the maximum values for L. It is goes from negative L to positive L. And what this does, it describes the shape of the orbital in the 3 dimension. M's of L take values from what? From M's of L to M's of negative L to positive L. And we use those to represent, or we indicate. So if we have the first letter represent the principal energy level as represent the m's of L, we can do this. Therefore, energy level can be used to describe those. So when we say 7F, you know what those are represent. We can use those to represent. Table 6.2 summarizes the number of, all the 4 quantum numbers with the possible values for m's of L, the number of sub-labels, the number of orbitals that N, value for N0, and then we have 1s, 2s, and 2p. This is used for what? For writing the electron configuration. Later on, we'll see how we use this to write electron configuration. For quantum numbers, if you are given a question, what are the possible values for L if N is equals to 4? In this case, you need to know that the angular momentum takes values 0 all the way to N minus 4. N minus 4. We don't have 4, so it can be 0, it can be 1, it can be 2, it can be 3. Well, I see, the possible, this is possible, but when I look at this, what is wrong is 4. 4 is included, it cannot have 4, and this one is impossible to have 5, even 4. So the only one here possible is B for possible values for L. How many different values for m's of L are possible in 5F? This is sub-level. So if we have the values which are the orbitals, how many orbitals are in any F? It's not about F, and F is only, 5 is only the principal energy level, but the sub-levels here, based on what we have here, if we have a sub-label for all the F, whether it is 4, whether it is 5, we have 7 possible values for m's of L, m's of L.
Will we be given that chart to use, or do we need to memorize that?
You need to, this one you can generate this to from the very beginning, that if I know M, what will be the possible values for L? What is the possible value for m's of L?
I see.
Right? Yes. So the only way is to learn how to generate the L values from the N value, because you can be given any. You are asked to determine the sub-level. There is the last quantum number here we call the spin quantum number. We define the orientation of, the spin of an electron within the orbital. The spin quantum number here, m's of S, equal this divine the spin of an electron, and take values only plus 1/2 or minus 1/2. The spin quantum number, I know I had not talked about this. It defines the spinning of an electron. You have seen this. Notation that when you use orbital diagram to write or draw the electron configuration, 2 arrows will never point in the same direction. One is pointing down, one is pointing up, because of what? Because of the spin quantum number we call m's of L. Here, the shape, angular momentum, you need to know each one of them. I gave you earlier on that N represent the energy. All right, here, principal energy, this is the principal, represent energy. The angular momentum represent the shape. all right? L represent the shape, which is the angular momentum for these principles. This is the energy. The M's of S represent the spin. This is what I just mentioned, that the M's of S define the spinning of an electron, and spinning is when they are in an orbital. You know, when we write that, they represent an orbital where electron reside. It cannot take more than 2. There are dash orbitals in the third diagram. How many orbitals? In the third shell, the number of orbitals. Here is the number of orbitals equals to 3. This is the table where we are talking about the number of orbitals. That we have 9 orbitals. If you, in case you are given any in any energy level, which is n, in this case, it is given by n squared. So if that is the case, 3 squared equals to 9. 3 squared equals to 9, just to give you how you determine the number of orbitals. So if n is equals to 4, then it's gonna be 4 squared. If n equals to 5, 5 squared. If n equals to 2, 2 squared, which is 4. That's how to find the energy square. And the number of electrons. Energy level is given by 2n squared. If n is equals to 1, then it's equals to 2 times 1 squared, which is 2 electrons. That's the maximum number of electrons it can go in there. Just give you that. There is a summary on how to find the number of electrons. Read more make your own notes on those quantum numbers, what they represent, how to figure it out that. This section 6.6, the shapes of the orbitals. I know you covered this. The dumbbell, I'll leave section 6.6. Dumbbell for S orbital, this shapes. They are spherical, like that. Whereas you see this spherical, it is L, like a sphere. Dumbbell for the p orbitals, dumbbell. This is just a probability of finding an electron for 2s, the 3s. I will not ask you to draw the spatial for 3s, 2s. But what I want you to know is the shape of all s orbital, whether it is 5s, whether it is 4s, they all have spherical shape. Now for all p orbitals, all right, p orbitals, they are what? You know what they are. And you may see in 3 dimensions, if it is on y-axis, you may see px, py, or pc, depending on the orientation on the 3D. But this is dumbbell shape. It's a dumbbell shape, whether it's 2p, 3p. This is what you will see in terms of the orientation in 3D. If it is lying along the y-axis, we call it py. If it is lying along the x-axis, px, and p PZ, if it is on Z axis, There are three of them. Remember the three two loops, which is 4 loops for the Ds, and this will be another layer. Let's see. You'll see this on a spherical. How many or what is dash orbitals are spherical? This is A, S. They are spherical. These are damper. These are curved. Mentioned that. Now, in preparation for electron configuration, this is the arrangement of sub-levels from the nucleus, energy level 1, energy level 2, energy level 3, all the way moving away from the nucleus, moving away from the nucleus. One, in energy level 1, we have 1 sub-level. In energy level 2, we have 2 sub-levels. In energy level 3, we have 3 sub-levels. In energy level 4, we have 4 sub-levels. And these are, look at the pattern, 2s, 2p. And each one of them, they are, P, C, P, X, and PY, 3s, 3p, and 3b. This will be helpful when we write the electron configuration. There is a way we use this, but arrangement, if you look at the energy level, you get to what? You get to 2p before going to 3d. This is how each of these orbitals are occupied, moving away from the what? Moving away from the nucleus. For a nitrogen, it will occupy the 1s. For helium, it will occupy the 2 electrons. For lithium, 2 electrons will be here, and then the 1 electron will come here. So you move away. It will not go to 2p forward before the 2s. So you go along when you have more electrons. We call these degenerate orbitals. That means they have same energy. This term right here, degenerate, means have same energy. That means they occupy. These have the same energy. We're gonna use this in writing the electron configuration. Now, this pattern here, I don't want you to memorize this diagram. If you want, that's fine. If you can reproduce this, this will help you. But how do we write now the electron configuration of an element? This is what I want you to learn. In first energy level 1, we have 1 sub-level, and that is 1s2. The superscript stands for the maximum number of electrons. In energy level 2, I do have 2 sub-levels, 2p2, and we call this 2p what? 2p6. There is a pattern here. It is increasing by 4. The maximum number of electrons is increasing by 4. So if I get to third level, there are 3 sub-levels, 3s2, 3p what? 3p6, and 3d10. If you look at the pattern increasing by 10, 4s2, 4p6, 4d10, and then 4f14. It's increasing. The maximum number of electrons is increasing by 4, 4, 4, 4, 4. If I get to 5, 5s2, that's the maximum number of electron. 5p6, maximum number of electron. 5d10, maximum number of electron, and then 5f14, and then it goes on. I should have 5 on the 5th, 6s2, 6p6, 6d10, and 6f14. If you have this pattern here, you can write the order in which sub-labels are occupied according to increase in energy. If you look at where my cursor key is, the order in which these orbitals are occupied by electrons has to do with the energy level. In other words, electron will occupy 4sp for 3d. 3d will be occupied by electrons p4 forward, p4 4p sub levels. How are you going to make sure that you are doing the right thing? You can use a diagonal arrow to draw this 1, 1, that is by itself, 1s, 2s, and then you change the 2 here, 2s, 2p and 3s, 3p and 4s2. So 1, 1, and then 2, 2, and then you change 3 here, 3d10 and 4p what? 4p 6 and 5s2. So if I go to this third level right here, it will give me the pattern by which I'll write electron configuration. So that if I change the head and the tail, change the head and the tail, change the head and the tail, if I was to start here, start and end here, right there, I can write this, look at this, 1s2, 2s2, 2p6, I'm here, 1s2, 2s2, 2p6, 3s2, so it's 3s2, 3p6. Watch this. Once we are in 3p6, you go to 4s2, which is what we have here, 3p6. That means 2 electrons here, 2 electrons here, 2 electrons here. That's the maximum number of electrons I have as a superscript here. And then you go to 4s2, and then you go to what? 3d10, the maximum number of electrons here. The 10 is because of this orbital, it can take 2 electrons. 1, 2, 3, 4, 5. That is the maximum number of electrons. And then you go to 4p6. You see 4p6, because each electron can, or each orbital here, take a maximum of 2. That is the 6 right there. Here, after 4p6 here, you go to 5s2. 5s2. And then 5s2, you go to 4d10. 4d10. And then what? 5p6. 5p6. And 6s2. 6s2. Remember, the superscript stand for the maximum number of electrons. What I do have here, I've summarized here. This is an increase in energy right here. Electron will occupy the lowest in energy level before filling in there. Common mistake if you took chem or introduction to chemistry a while back, or if you didn't take, student will think that you electron go to 4s before 3p, or they fill in the 4d before 5s. It has to do with the energy level. There is an overlap. There is an overlap. And the way I'll make sure is learn how to reproduce this to write electron configuration for multi-electron system. This is with respect to what? With respect to hydrogen. With respect to hydrogen, that it was single, but for multi-electron systems such as what? Helium, such as lithium, such as sodium, we can use this pattern to show how the electrons are occupied. So these are the degenerate orbitals. These are the degenerate orbitals. They have the same energy. With this pattern, we can now write the what? Right electron configuration of right electron configuration. This is just the spin quantum number showing how electrons spin when they occupy the same orbital that they spin in what? In opposite direction. The spin quantum number represents how the electrons behave in an orbital. I used earlier on the two arrows. This shows opposite spinning. Now with this, we are now ready to do what? To write the electron configuration of, electron configuration of element on the periodic table. But before we do that, there are two rules. There is the Hertz rule and there is Pauli's exclusion rule, which states that no two electrons in an atom have the same four quantum numbers. That is principal, angular, magnetic, and the spin. All these are the the three quantum numbers or four. 1, 2, 3, 4. This means we cannot have the same. They must differ in a way. With that, we can write the electron configuration, which is basically the way electrons are arranged around the nucleus of any element, occupying the lowest energy level before filling in the energy level. And there are three methods. One is using this 1s2, 2s2. Using this is one method. Let me just even write here that this is method 1 of writing electron configuration. You reconcile the superscript numbers with the atomic number on the periodic table of a particular element. For example, if I want to write electron configuration for hydrogen, which is number 1, all right, it is just 1s1. I don't write 2 because it is atomic number 1. But for helium, it will be 1 what? I need 2 electrons. If you look at lithium, this is 1s2, y2, because I'm done with the first shell. You go to 2p1, not 2p6. It's not 2p6 here. No, 2s. Not, I meant to say 2s. 2s1, not 2s2, because lithium is number 3. This is number 1, this is number 2, this is number 3 on the periodic table. Let's see something else such as sodium, which is number what? Number 11, I'll say 1s2, 2s2, 2p6, I have 10 so far, and then 3, not 3s2, but 3s1. 3s1. So you'll reconcile the numbers here at the top here with the atomic number of element in question. And there is no way you can generate this unless you master this. This will help you in coming up with the order in which the sub-labels are occupied by electron according to increase in energy. Any question on method 1? This is the long way. You need to know this, all right, so that you can write the electron configuration of an element. Method 2 is, no, you can do that. Method 2 here is orbital. Here too, this is orbital filling diagram, which means you'll be given this 1s, 2s, and then 2p. Look at 2p. 1, 2, 3, and then 3s. So that if I'm writing the electron configuration for helium, it will be 2 electrons facing opposite direction. You cannot pair them up. When 2 electrons occupy the same orbital, they have to have opposite spin according to Hund's rule. If it is lithium, for orbital filling diagram, if it is lithium, let's say lithium, all right? Lithium is number 3. So I have 2 so far, and then it can face up, it can face down, so long as you have 3 arrows. Arrows represent electrons. And the number of electrons should correspond to what? The atomic number. So if we, let's say sodium, I'm gonna do sodium here. If I have sodium, which is number 11, I'll have to account for 11 electrons. And you see what's happening. So I have what? 3, 4. Look at the degenerate orbitals. They are singly occupied first before you start pairing them up. So 4, 5, 6, 7. You don't go there. You come back and start 8, 9, 10, 11. You have to singly occupy first the degenerate orbitals before you start pairing them up. All right, that's what you need to know, an orbital filling diagram. This will help you in, we're gonna talk about in chapter 8, paramagnetism and stuff like that. You need to know how to use orbital filling diagram using the arrows and the dashes to represent. So if it is 3D, you have to know how many dashes you have. 1, 2, 3, 4, 5. And they are singly occupied before you start pairing them up. So that is orbital filling diagram for electron, method 2. And then method 3 here, the last one here, we call, I can say shorthand, whichever way you want to call it, or noble cast electron configuration. Noble cast, we use group 8. You know the noble, right? The group 8 on the periodic table, which still, you need to know the first one. This one right here, let's say, for example, here is electron configuration for sodium. In the third method, you look at the what? You look at the element in question, co-pack 1 row above it, go all the way to group 8. And in sodium, the closest group 8 is neon. You go back 1 step, 1 row, and then you go all the way to group 8, the noble cast. Look at the noble cast and put it in parentheses and understand how many electrons does that noble cast represent. This will be what? This will take care of the first 10 electrons. These are the 10 electrons, and it is represented by this neon. This is the shorthand. So in that method, we'll have this for sodium 3s what? 3s1. This is the shorthand method for writing electron configuration. So if we have, let's say, chlorine, number 17, this is number 17 on the periodic table. You'll have 1s2, 2s2, 2p6, this is 10, 3s2, that is what? 12. We need 5 more. So 3p5, not 3p6, 3p5. So if I'm to write the shorthand, neon has what? 10 electrons and then 3p5. So you need to know the longer one before you come up with the shorthand electron configuration. Shorthand electron configuration. I know if you write the ground state for all of them, you can do that. So remember to write what? If you look at this notation, you should understand where it's coming from. I explained in earlier on this the mnemotic way of remembering. This is the maximum number of electrons, which can go in 5b. We can use that to what? The superscript represent electrons. You see here, superscript represent electrons in those orbitals, which is what you will need. This means energy level 4 and it has 5 electrons. Any question on the 3 methods of electron configuration? Orbital field diagram for lithium, you just have to represent electrons using arrows. It shows the spinning. So this one, the one on my whiteboard is the long one, or I call method 1. I call method 2 here. So I could have for lithium, what you see on the screen for lithium could be like this. 1s2, 2s1. This is 1s2, 2s1. Still, you need to know that. And then the shorthand, of course, which we have that shorthand is using group 8.
Can you go back to the shorthand where you have neon? I just want to clarify something.
Right here?
Where you had neon and then 3p5.
Right here?
Since neon covers 1s2 through 2p6.
Oh yeah, honest to 2p6, yes, 3s2. Yeah, you're right about that. This is
okay. So we are supposed to write 3s2, 3p5.
3s2 and 3p5. Thank you.
Okay, perfect. Thank you.
So 3. You're right about that. Thank you. Any other question? So there are 3 methods which you need to know. You got to be well-rounded in all of them. Question could come in any way. I've seen question where it is kind of like, somebody may think that we have only one way of writing electron configuration and you are given which one of the following is the electron configuration of sodium, and you have A and B being correct, and then you have to know that they are one possible. Question always will not be write the electron configuration, You can be asked, identify the element represented by this electron configuration. So if you know the superscript numbers represent what? Represent the total number of electrons. You just have to add the superscript numbers reconciled with the atomic number and say this is the element. You gotta be careful that which one of the following is the correct way of writing electron configuration for neon. If I flip, all right, if I flip the numbers here, just write 3p5 and 3s2, that is wrong. Somebody might just pay attention to adding the superscript, forgetting that the order also do matter. The order, you cannot flip the numbers. I cannot have 3p5 and 3s2. You'll add the superscript, it will give you 17, and you will get it wrong if you don't do your homework right. As far as electrons configuration are concerned, we have what we call the abnormalus, or before I even doctor, let's see the learning check here. The lowest energy level is reached when the maximum number of electrons with the same spin is. This is a statement of Hans rule. It was just right here. Yeah, they you don't pair them up until they are singly occupied. So the condensed, this is just the group 8. Condensed is the same as, the shorthand, the one I was telling you that we use group 8. You see this helium for lithium, sodium, neon 3s1, potassium. And the criteria by which you pick group 8 is you look at the element in question, go one row above, go all the way to the end, see how many electrons are represented by that in the condensed. So what I was pointing is there are some electrons which do not follow this pattern. We call the anomalies. Anomalies are abnormal. Anomalies are abnormal, all right? And the first study is chromium, number 24, and copper, number 29. Within the first that elements, these are electrons do not follow. Typically, if you write the same, you will end up with this is D4 and D5. Let's say we write the electron configuration of chromium. What do I mean by that? For chromium, number 24, this is 1s2, 2s2, 2p6, all right, 3s2, that is 12, 3p6, 18, 4s2, 20. You expect this 3d4, right? And that is how you write. But it turns out that you promote this. This is abnormal, that it will be 4d5 and 4s1. It is abnormal. We call this, if the last one is d4 or d9, you promote this to 5 and make this 10. The first to or within the first 30 element on the periodic table, only chromium and copper have 3d5 for chromium, and for copper it is 4s1 and 3d10 for copper. It's abnormal, and this has to do with the stability of the atom. It has to do with the stability of the atom. There are terms here which I want us to carry forward, moving forward. When we talk about the valence shell, that is the outermost shell, we call the outermost shell valence shell. Outermost shell. And the electrons occupying that outermost shell, we call those valence electrons. Valence electrons are shown using the, they are outside. We're gonna talk about in chapter 7 about the valence electrons and how they impact the properties of element. Group 1, they have one valence electron, group 2, and so forth. I know you can recall from that. Other than that, that marks the end of chapter 6. That's what I wanted to bring to your attention. Let's see this before we call it a day. The ground state configuration of fluorine, of course, we are now coming in with the condensed or noble cast or shorthand, that we go back one step, and if we go one step forward on chlorine, I see it is helium. So helium will account for what? Will account for 2 electrons, and the remaining one to make fluorine number 9, we need 7. We need 7. Is it 7? Yes, 7. So if we add 4, this will not give us the correct answer for the number of electrons. No. If I look at this, this is B5, the correct answer is D. So this is possible ways you can be asked for that. This was, the transition using the shorthand. Sync, of course, D10. You know how that one is going through for that. All right. Be careful when you do that shorthand. And I say there are 2 orbitals which there are 2 elements which do not follow that. Other than that, please read on those, and that's what I wanted you to know in chapter 6, writing the electron configuration for 3. Yes, Jason, you need to know the 3 method because question can come from either way. And some knowledge in chapter 8 will be handed that if we only learn one, in chapter 8 we will be expected, or chapter 9 will be expected to know certain electron configuration in order to move forward with certain terms and concepts we will need. When we talk about paramagnetism, diamagnetism, we will be using the orbital filling diagram to see that single electron, all right? So you gotta be careful with the 3. Any other question? What I want to do is I will make quiz, before we call it a day, I will make quiz number 6 available due on, you have to do before taking the exam. You have to finish chapter 6 quiz, homework as well, so that you do well in the exam. I would like to, today is Tuesday, I would like to make the quiz feedback available on Wednesday night when we meet on Tuesday, on Thursday. If you have any question, you can ask, or you can send me an email before we meet on Thursday, so that at least you get to learn out of the mistake you will make out of the questions. Some of you can figure it out, all right? Other than that, as I said, please take seriously the mock exam Nick prepared for you guys. It pretty much covers the same concept you'll see in the exam. Other than that, the class is dismissed. I'll see you again. On Thursday. Somebody asked a question.
Professor,
Yes.
you kind of showed a slide with the lanthanide and actinide series on there, and then you kind of said read it. Like, do we need to go in the textbook and understand and memorize all these F orbital things?
No,
or is that not?
Lanthanide, that will be taken care of. You see, lanthanide, you have to account for the F, right? So if I know where the F is in this diagram right here, it's just gonna come down again right here when you go back, and it will take care of the lanthanide series where you go with that. Okay. All right, thank you. So lanthanide will account for the F flux. You see this, which if you follow this pattern, what next? You're gonna occupy the 4F. Where is the 4F in this diagram? It will account for this. You will never go wrong with this diagram in any electron configuration. So if that is the case, somebody has a question, mock exam 4 p.m. tomorrow. Yeah, somebody saying, yeah, please take care of, be honest, do that. I'll give you all the constants you need. The class is dismissed. I'll see you on Thursday. Thank you.